Greetings, everyone. Hello, good morning, good afternoon, good evening, wherever you are in the world. Welcome to Photonics for Quantum 2. My name is Don Feiger, and I'm your host. And we have an exciting program this week. We had an excellent talk yesterday, and we have an interesting twist today. It's a government panel. We also have another panel on Thursday called Women in Quantum. Otherwise, we have science talks for the rest of the week. And I think we have a poster on Friday. So before introducing our speakers in this government panel, I wanted to give thanks to our generous sponsors whose logos you see surrounding me and whose generous contributions allow us to deliver this content for free to you. As you know, you can get the recordings of these talks by going on the PFQ2 website and clicking on the talk title or the author name, at which point a little accordion box will stretch down and you'll be able to see a link to the video and to the slides. Okay, so let's move on to today's speakers, multiple speakers in a panel, and I'll introduce them in alphabetical order of their federal agency. So the first person on the panel is Babak Saif, who's from NASA. He's a senior optical physicist. He served as the optical branch head at NASA, and subsequently he also worked at the Space Telescope Science Institute when I first met him, which was years ago when we thought JWST would be launching relatively soon. It still hasn't quite launched, but hopefully when it does launch, it'll be very successful, just like the Hubble. Babak is the senior optical physicist with Goddard's Instrument Systems and Technology Division. There's Babak there. Hello, Babak. The next person is Carl Williams, who's the deputy director of the Physical Measurement Laboratory at NIST. And he directs the Quantum Information Program and helps lead the National Strategic Computing Initiative at NIST. Hello, Carl. He's a member of the executive leadership team within the Physical Measurement Laboratory, and he represents the PML to other federal agencies. The next is Dominique Desjardins, who's the program director at NSF for Electronics, Photonics, and Magnetic Devices. She got her PhD just down the road from here at University of Rochester, and she's worked on sensors and worked in the French Atomic Energy Commission, and has been involved in lasers and light generation for her research career. Hello, Dominique. So why don't we start out with each of you giving a few slides that you've prepared, and hopefully they'll describe some of the interesting things going on in your agency in the area of quantum. So Babak, I don't know if you're able, but please try to share.
Okay, so let me click on the thing and then.
There, we can see your slides and we can see your video if you want to go ahead and start the slideshow.
Okay, good. Okay, thank you for inviting me. I just wanted to, this few slides sort of covers in a very general way what NASA has been doing in quantum related technology, and these slides are not mine. I asked Michael C. Bloom, who's the chief technologist for SMD, to send me these slides, and I want to use, and I picked a few of those, and I want to give you a little bit of a feeling what is going on at NASA. So one thing that we have been sort of involved at, it is in a space, and lots of nice things are happening in that laboratory, is the Cold Atom Laboratory on ISS, International Space Station. And the goal of this laboratory is to demonstrate cold atom technology for cold atoms over Bose condensate, atom interferometry, Bose condensate interferometry, and those kind of topics are related to atom optics, and this has been working, and lots of the students are working with ISS to do experiments in space. And I think right now they're in a second phase or third phase of this project. Also, NASA has been involved with, we like clocks, of course. And NASA actually did launch a deep space atomic clock, which is a mercury trap ion clock that is in space right now. And so we are also interested in atomic clocks and their application maybe to the science for long baseline interferometry and all that. In this slide, we also very much interested in gravity measurements. As you know, 96% of the universe is sort of unknown to us, and mostly are gravity related, dark matter, dark energy. And we generally, when we do gravity measurements for Earth science or otherwise, we have two spacecrafts that they have a base follow and lead kind of configuration. The relative velocities between these spacecraft changes, and from that we get a map of the gravity field, whatever the gravity field is, whether it's a time varying, static. But we think that use of the atom interferometers, use of the laser cooling techniques to build atom interferometers, that they are science instruments, not just for inertia measurement, inertial force measurements, but they are science instruments that they go way beyond just the inertial sensors. So these devices based on atom interferometry, they can replace two spacecraft like GRACE, two spacecraft GRACE with one spacecraft, and they can do maybe 100 times better than sensitivities and spatial resolutions, factor of 3 better than GRACE. So these are based on atom interferometry. So here, what we are utilizing, what we are using is the superposition state, superposition resources that the quantum mechanics offers us to do much better sensors. And these devices are used in the inertia frame to do science, as opposed to the same kind of instruments can be done in a non-inertial frame to measure inertial forces, but not to the level of sensitivities that this one's that we are developing right now. These are going to be used for stochastical gravitational wave measurements, dark matter measurements, and very, very fine gravity measurements. We're also interested in what can we do to improve our classical sensors, but using quantum receivers. So in this kind of a approach, we are not really sending a non-classical light out as a sensor, as a sensing, but we are actually manipulating the classical light that comes back with the quantum resources to be able to go beyond what we can do classically. And for one of these things that we are very much interested using a quantum receiver is universal telescopes, that we can actually go way beyond Rayleigh's criteria and have specific tasks for the telescopes to do using quantum resources. And finally, and we are also recently have become very much interested because of the requests by other agencies that we will be able to provide entanglement sources in space for the space ground and space-to-space quantum communication. And the goal, hopefully, is to be able to provide a space link to our partners for intercontinents in about 7 years. And that's a new project for us. And I think that's the most serious project that so far NASA has embarked on as far as the quantum sensors or quantum communication is concerned. Thank you.
Okay, thank you, Babak. I have a few questions for you, but I'll just wait till the end. And so let's pass it over to Carl Williams at NIST.
Okay, there, I think my slide should come up.
Yep, we see him.
So again, I want to pass through a few slides. I'm going to do this relatively quickly. It's interesting on this panel, the three government agencies, because you have NASA, which is kind of an applied agency that does funding in support of its mission. You have NSF, which is very much a fundamental basic research agency that funds a tremendous amount in the physical sciences. And then NIST. This is predominantly not a funder. I will talk a little bit about the funding we do. We are a mission-driven agency whose goal is really to create the measurement infrastructure for the United States. And as such, we set those definitive standards and we make measurements at the state of the art. And having said this, the state of the art today often requires our ability to manipulate the quantum world. So this is what we do. One of the things that happened actually in 2019 was basically the redefinition of the metric system. This was an effort that NIST worked with the international community and the Treaty of the Meter, the organization of the Treaty of Meter, to basically redefine the SI to enable high technology. So as a mission agency, we see that quantum information science is core to our mission, especially in physical measurements. It is basically the foundation of much of our best metrology today already. And so we continue to do that foundational research to push the state of the art of measurement. And I'll talk about how that has contributed to our expertise in quantum information science. We're also very much interested in engineering and improving the robustness of prototypes, because a lot of the stuff that we have that is true state of the art is a very large tabletop or special equipment, and it can't be put out into industry, onto a shop floor, in a car, or other things. And so engineering those systems to make them more robust allows them to be used by industry and also for our comrades at other agencies like NASA. And lastly, because the metric system or the System International, the SI, is one of the things that we're responsible for, we are using it to realize and disseminate the units of measure. So all these are interrelated, they feedback on each other, and we push things very hard. So I wanted to talk a little bit about the kind of funding we do. Again, we have two joint institutes. Both of these are very large. Both of them have a quantum focus too. One is at the University of Colorado, known as GILA. And then we have both the Joint Quantum Institute and the Joint Center for Quantum Information Computer Science at the University of Maryland. And in both cases, those are also partnerships with NSF. And so, again, we have strong relationships with the other agencies in those joint institutes where we embed some of our scientists to actually have a forefront out into the world of science and understand where the technology and concepts are going. One of the things that we were tasked to do under the National Quantum Initiative was to basically build, to create the Quantum Economic Development Consortium, a consortium of industrial players to help build the foundation for a future supply chain for the quantum economy. And so this is one of the things we have been doing. This is now being formally established and everything else. You want to learn more about it, please reach out to Joe Broza, Celia Merzbacher, and they'll tell you about it. There are more than 100 US companies are now engaged in this consortium. So again, all the companies from laser companies and cryogenics to the big companies that are trying to build quantum computers or quantum network components or other things. So very, very exciting thing to do. So our program is just like the whole of quantum information science. I mean, QIS, you can do improved sensing metrology, you can do secure communications, you can do simulations, you can do computing. And we actually have a program that covers all these areas. Our formal program actually goes back all the way to 2000. but the first paper dates all the way to 1992. This was Dave Wineland who basically proposed create certain exotic states of atoms to build better clocks all the way back in 1992. In fact, we had the first workshop that was solely focused on quantum information science in 1994, shortly after Peter Shor came out with this algorithm. So why was in this position to do this? Well, again, we have a long history of manipulating quantum objects. The volt has been defined by the superconducting Josephson junctions since 1990. And so we have been building those for 30 years. We're one of the only NMIs to basically show that you could do all the legs of Ohm's law, improve V equals IR, absolutely, by counting single electrons, using Josephson voltage, and using quantum Hall effect, and basically prove that that law holds to a few parts in 10 to the 7th. Nobody has ever managed to do that. Really long, difficult, hard job, but something that we did more than 15 years ago and abandoned at that time because it was too hard. We consider the power of one quantum bit to be an atomic clock. Here's the quality of our atomic clocks. The blue dots are microwave standards. The red ones are optical standards. Today, the optical standards are far more stable, and we expect that there will be a redefinition of the second sometime in the mid-2020s. This is, again, a discussion going on within the international community to redefine the second, because we can actually do better than we can currently do with microwave clocks. But we've been doing this for a long time. So power one qubit, nothing but an atomic clock. I point this out because, and I want to show some data from Dave Wineland's group going back to 2010. Now, this is a decade old, but in 2010, we were already doing quantum logic to run one of our clocks. In fact, this is the single place where I know that quantum logic has been used for more than a decade. We use it to build and run one of our clocks. What's shown on the left is that if you have an ion in an ion trap and you start exciting it in that ion trap to high emotional states, because it's moving, it ticks slower. And therefore you see special relativity. What you see in the right is you see the blue and then you see the red dots. And what you see is first the clock is sitting on a table. Then we jack the table up 30 centimeters, about a foot. And you can see that it ticks at a different rate. Why? Well, it's in a different gravitational potential. That is general relativity of impacting our clock. Today, we can see less than a centimeter in our best clocks. So the fact is they provide exquisite means of sensing the environment and other things. Again, something we have done and played with for years. We were one of the first to do high-speed quantum key distribution and made a lot of progress on that. And it really drove us to do create single photon detector technology. So I mentioned that, and it goes back to, ties back to NASA, because again, we built the sensor arrays for the Atacama Cosmological Telescope, which measures the microwave background. Again, this comes out of the same technology we used to build our single photon detectors that are now almost 100% quantum efficient, better than 99%. We've used those detectors to basically close the Bell state loopholes and to basically create random bits. Again, because of IT standards and everything else. So one more final slide, and this kind of ties back to Babak. We're very interested in working with the other agencies and other things, because our clocks are now to a point where they almost are not even suitable for use on the planet Earth. But a network of clocks in space will allow very long baseline interferometry, improved telescopes, perhaps gravitational wave detection, and other things, state-of-the-art measurements. And of course, we won't ever be able to do those state-of-the-art measurements without the other agencies. And of course, this also goes back to NSF, because they really focus on the basic research in that agenda. And with that, I'm done. And I hope this kind of gives you a view of our interest. Thank you.
Okay, thanks, Carl. That's fantastic, very exciting, and thanks for also describing how the three agencies are sort of framed differently in sort of their structure. It is interesting that they're all different, and NSF perhaps is the most different from the other two. So Dominique, if you could take it away and show us your slides.
Certainly.
I can see your slides.
Very good. So I want to try and tell you a little bit about NSF, and indeed it is a different agency in that we typically fund fundamental research, and NSF has been funding quantum information science for decades, but in 2017, our director then decided to put forward 10 big ideas that were bold ideas in advancing fundamental science, and one of them is what we call the quantum leap, which is one of the research ideas that was put forward. And we have had quite a fair amount of activity in the area of quantum. And really what the quantum leap is meant to do is to bridge the gaps between the fundamental science, the next generation of devices and technology, and future quantum systems, and being able to have them feed into each other to advance not only the fundamental understanding, but also hopefully the technology that is needed to advance the field. So we actually put together this Quantum Leap working group that encompasses all the directorates within NSF, as you can see with those check marks. And we've had a large number of funding across all of those. But as you might expect, decades ago, that the funding came mostly from the physics community, whereas now it is really meant to cross-cut all the different fields. This slide is a little old in that it shows Franz Cordova as our director. We actually have a new director, Dr. Panchanathan, who just started this month. So I'll need to update that next time around. I don't have a picture of him. But here is what we plan to do with this quantum leap. We want to, as mentioned actually by Carl and Babak, we want to collaborate very tightly with other governments, labs, and industry. And I think it's very critical in the area of quantum information because it's so broad and it requires a lot of expertise from different areas, and each agency has its strength. And by working together, I think we can really advance the field very dramatically. We also want to use convergence, which is getting people from very different disciplines to work together to get to the point where the science hopefully moves out of the lab and into actual scalable practical systems. And we want to develop the workforce that is needed for this science to move forward by educating students across the different disciplines. So this is a slide that shows the different programs that we developed under this initiative since 2016. And if you start from the bottom left, the EFRI Acquire was actually an engineering-led competition that is meant to move beyond the frontiers of research and innovation. And it focused on communication in the area of quantum information. And we funded 9 teams that are still ongoing right now and have produced a lot of very interesting breakthroughs in the area of quantum communication. We've had a couple of solicitations to expand the workforce. One that we call Triplet, which is, as you can see, it was started by NSF, but is actually also supported by 2 other agencies, is to allow students to intern in either government labs or industries to actually get hands-on training in the area of quantum information science. And we also have had a quantum science summer school that we plan to expand beyond this year as well, that has been cross-disciplinary and has allowed students for 2 weeks to actually get training across the discipline. The third item that I have listed here was this Ideas Lab, which was essentially asking the community what would be the most practical way to develop a fully connected quantum computer. And we wanted to look at the full stack from the material device protocols and system level. The Ideas Lab resulted in one large grant that is called STACK, actually, a lot of acronyms. The QMAs is another solicitation to the community on trying to respond to some of the questions that many people had, which was the issues of getting the appropriate quantum materials to allow advances in the area of quantum information in many of the different platforms that were not as robust and mature as the superconducting platforms that you heard about. And so we have had one grant to Santa Barbara where they have started developing a foundry for those new materials and devices. In parallel to that, we had a fair number of smaller grants that were meant to test the community on new ideas, current challenges, new ideas to advance quantum information. We called those incubators, and this went on for 2 years, and we have over 30 teams working in the area of incubating different ideas across multiple disciplines, from bio to mathematics, physics, engineering, chemistry, and has been very productive. And we have what is going on right now, which is our Quantum Leap Challenge Institute, which is actually in response to the National Quantum Initiative, where NSF was asked to support new centers in the area of quantum information science. This year, it was our round 1 of competition. The competition is closed for this year, but we will have round 2 next year, starting with letters of intent this month, actually next month, and continuing into next year. This is our big centers. They are meant to be funded at about 25 million per institute, and we hope to fund several of those between the round 1 and round 2. And last but not least, we have recently put out a call for what we call convergence accelerators. And one of those tracks is on quantum technology. And it is meant to probe the community in areas where the technology is actually ready to be deployed within a few years to some degree in forms of prototypes. And hopefully there is interest from academia and industry that can work together to advance that technology into an actual devices. So those are the activities that we've had for the past few years, and we continue to work on some new ideas for the coming years. And I just want to leave you with my contact if you have any questions, and any questions specifically related to the Challenge Institute. I would recommend that you contact directly the QLCI at nsf.gov.
Okay, thank you, Dominique, and thank you, Babak and Carl, and I'll clap on behalf of all the muted participants, who I'm sure are silently clapping right now. We have plenty of time for questions from the participants, and I had a few questions myself. So typically it takes maybe a few minutes for people to type their questions. And while they're doing that, I wanted to maybe ask some myself. And what I'll do is I'll put it in the chat window, but I'll also read it so you don't have to go hunting down in the chat window. So what's the relationship between your organization and OSTP? And one way to interpret that is what is the information in the strategy document that's there now that you take, that's a mandate on your agency? There's the national strategic overview from OSTP. Is that binding in any way, or what is that? What information does that give you?
So again, NIST and NSF, along with DOE, are co-chairs of an interagency working group that has helped create those documents. So when OSTP publishes something, it's publishing something that the agencies which are at the table, and in fact, all the agencies on here are at the table. Again, NIST and NSF co-chair it along with DOE, but we're trying to decide what the high-level questions and policy goals should be for the U.S. government to move an agenda forward. And so we all support those goals. We all have, again, a slightly different mission space, and we approach them in slightly different ways and accomplish them. But OSTP represents us, and we represent them. So it is a team relationship.
Okay, and I take it that Babak or Dominique, you didn't want to add anything further to that? So the next question is, these questions are random, I think in sort of random order, random importance. And it's in regards to international collaboration. What is the interest, if there is any, in international collaboration in your particular agency? Dominique, do you want to take that?
Yes, I'll answer mine because the answer is going to be very short. NSF does not fund outside the US. However, we have had some supplements that we have given to our own US grantees to spearhead collaboration with international entities. And we are very interested in having some further collaborations. So to us, it is something very important. Since we cannot fund researchers, international researchers, we can only offer supplements to our own grantees. But what we do allow is collaboration, and what we hope to do is also collaborate with other agencies who can fund outside of the US.
Mariko Osinski is asking if Canadian collaborators are funded by NSF, but Canada, at least for now, is not part of the US and so cannot be funded by NSF, right?
That is correct.
So I can say a little bit about NIST. I mean, again, because we are part of measurement infrastructure and the metric system is an international agreement, we work internationally. You know, we have a counterpart agencies in many, many countries. We know them, we work with them, but we also work with the scientists in other countries as well. If you come onto the NIST campus and you look in my laboratory, there's roughly 1 to 1.5 additional people for every federal employee. And of those 1.5 additional people, half of them, 0.5 or about 30% are foreigners, and they come from our NMIs and from universities abroad, and we work with them closely and everything else. So we have a very strong international engagement. We help push the world's measurement system forward and work with redefining the metric system, as I said, with international parties.
So if we recognize that there is quantum expertise in certain countries outside of the US that is equal to or exceeds our own expertise, then what is the way for our nation to leverage that?
So again, with regard to the broader industrial piece, the consortium that's been set up will have international participants. And we've set up a structure to engage broadly, because supply chains today are global. The world economy is global. I mean, it is not a single country cannot do anything largely today without the broader industry. So we see that, we understand the value of working with the experts in other countries. And again, you know, some laser systems, depending on which ones you want. For some of them, you go to Germany. For some, you get from the US, some the UK. They're all over the world. You go and buy components. You want to do this refrigerator? Half of the companies in the world, or more than half the companies in the world, are outside the US. So the supply chain for all the things we need to make the quantum world work is already international.
Okay, let's see. I have another. This should be an easy one. It's for small businesses to become engaged through SBIR or Tech Transfer STTR. Have you seen an uptick in the number of topics that are quantumish?
I think in NASA, actually, we do see that the increase is exponential. So NASA basically was not really taking advantage of the first phase of the quantum initiative. We were behind, and we still are. We are playing catch up. But as we understand things and as we understand our needs for quantum, we are creating subtopics for the SPIRs that are especially focusing on these topics that we really think that we're going to need for quantum communications, for quantum sensors and all that. And so as those subtopics are being generated by NASA, and we see a huge response to those subtopics. So yes, so we do see a large number of proposals toward these things.
Okay, and I presume that's true of NIST because Carl was nodding vigorously, and also NSF.
So for NSF, I would say, I'm sorry, Carl, I would say that we do not receive that many proposals in the area of quantum information science, although we have a pretty large SBIR STTR program. And I would suggest anyone who is interested in contacting NSF for SBIR, or STTR programs to contact the program director at NSF, Peter Atherton, who would be very happy to hear about the prospects in the area of quantum information science from the small business community.
And the only thing I will add is we get a fair amount, but our SBIR program is very small because we don't do a lot of external funding. And yet I can almost guarantee you every year there'll be at least one of the 6, 8 proposals that we fund that are quantum, if not 2 or 3 in some years. So we are heavily engaged in it, and we see it. You'll probably have much better luck getting an SBIR from NSF or NASA.
Okay, let's see this next question. I think we know the answer, or the answer that will be given, but I'll let Dominique give the answer anyway.
So I cannot say who won the QLCI competition for round 1. You will need to tune in. It will be announced very soon. It's
like they say, based on the advice of my attorney, I cannot respond to Congress, and et cetera. So I'll ask a slightly related question. In the early call, well, in the original call, I know there was some statement about NSF anticipating the idea of funding some number in the first round, some number in the second round. And I presume that the sum of the two was supposed to add up to roughly what the NQIA said, which was 5 or so. Is that still the thinking?
That's still the thinking.
Okay. And here's another question. Now, this is for each of you for sure. So here is for Babak. Maybe you can comment on this. What's the visibility of quantum to your upper administration? What's their enthusiasm for it? And how does it rank with respect to other priorities? For Dominique, that might be in relation to the other big ideas or perhaps it's the case where you love all your children and you can't say that any child is better than another. So, Babak?
Sure. So as Carl was alluding to, NASA is not really a research organization per se. We are very mission oriented. We try to develop technologies that we do need for a mission starting at TR level 3 and above. So our expertise is to rely on our partners like NIST and NSF that does the TR level 0s and 1s and 2s, and then we get them and try to use them for our mission and space qualify and elevate the levels of these technologies. So as I said, the first time the initiative of the quantum, we were not really big time included because we really thought that the TR levels are for these sensors are way too low for us, and we didn't really see the benefit to the sensors versus the complexity and the cost. But due to thanks to Carl Williams and externally, and also thanks to Audrey Yunus and Nasser Burgati, we became very essential in quantum network. So we became essential and became in demand to provide a space link for these quantum networks. And as such, the importance of the quantum and quantum sensors and quantum communication has elevated tremendously this past couple of years. So, so now we do have ear of our managers, and they do invest in quantum communication specifically and sensors in general.
Carl, did you want to go ahead?
So I would say the NIST director has been aware of our quantum program for more than 15 years. Again, it plays such a key role in us pushing our mission space forward, that measurement capability, that it's just being built into us. So it is not the only priority we have. We have others, but they tend to be the hot topics, whether it's engineering, biology, or material genome, or other related things that are relevant to our mission space. But quantum is up there. It has played a very, very important role. It continues to evolve. And I think, and this is partly why NASA has come to the table, is we look at what the technical limitations are for the most sophisticated technology that will come out in this century. And a large part of it will come from what I will call quantum 2.0, the second generation quantum technology, because the transistor and laser were quantum 1.0, and they're already in our smartphones and everything else. So this technology is going to be crucial to the future, and the NIST leadership fully understands it and supports it.
Okay, Dominique?
So I would say NSF has a history of funding some area in science for quite some time, and realize that the area of quantum information science is one that is not going away, because there are still a lot of challenges at the fundamental level that need to be tackled. So I would expect that quantum information science will remain one of the areas of focus at NSF. But I will mention also that we have a new director who just started very recently, and Dr. Panchanathan has not had a chance to brief us on what he sees as his top priorities in his future agenda.
Okay, we have a question from Tony Shu. Tony, I just unmuted you. You can ask the question if you would like.
Oh yeah, thank you very much. Yeah, just really wanting to know, like, the pandemic's gonna be around for a few more years. I know it's a very tough question. That maybe a lot of kind of have to see how the virus goes. it's not totally in people's control. And the funding for fundamental studies, would that be directed towards more application research? You know, it's because I can see that people want to, you know, if I want to study something very just out there, I don't see any technology sort of potential in the topic. So maybe I want to like avoid that, right? Because it can be a very long shot if any of the physics there can generate an application. So would the funding shifting towards more application related research? I think that's my question.
Okay, thanks, Tony.
So you know, I'm happy to start on this. I mean, from a NIST perspective, only about in the laboratory I work in, only about 1/6 of our research is basic research anyway. A lot of it is very, very applied, and again, our program goes from the basic to the applied. And I want to give one example of applications of this type of technology to biomedical, and that is single photon detector technology, which has allowed people to actually image brains and see neurons firing. We've used magnetics to do this as well, and built very special magnetic sensors. There's a company out in California now that's commercializing some of the magnetic sensors we have developed under this approach. So when I look at it, the basic research moves from there to building a much more sensitive device, which then gets used in an application to show whether it can commercially displace something else. So I see it as a continuum. And despite COVID, I don't think we're going to shift where our balance between fundamental and basic research, between fundamental and applied research, because we need that full spectrum in order to develop the best technology in the world.
So I'll take that on. NSF funds fundamental research, and that's not going to change. So we did have some solicitation in specific response to COVID this year. So we did set some funds aside for what we call rapid programs, which were really very short-term means to develop some techniques or instrumentation to solve some of the issues and challenges on COVID-19, but the rest of our programs remain what they are.
Okay, I don't see any other questions. And we're coming up on the top of the hour, so I think this is a good time to end things here, unless anyone else wanted to say anything further. Otherwise, I wanted to thank you all, Babak Saif, Carl Williams, and Dominique Desjardins. Thank you very much from NASA, NIST, and NSF. And like I said before, folks, you can see this recording by going to the PFQ2 webpage and looking at the program. Otherwise, we'll catch you tomorrow at 1 p.m. for another Science Talk. Thanks very much, everyone. So long.
Thank you.
Thank
Bye.
you.
Thank you.